Hi all, happy Nowruz, happy Ramadan, other holidays for those celebrating in your geographies. Today we are having with us Murat again, Google Cloud and data expert and machine learning expert from the Google Cloud team, streaming from Netherlands. Thank you, Murat, for your time. And we have Azizullah is co-host of this event. Azizullah is streaming from Tashkent, and he is a lead of Developer Student Club, also a champion of some competition for software engineers. And yeah, thank you for noting, Murat, this camera is full. And without talking a lot of introduction, we transfer mic to Murat.
Thank you very much. It's my pleasure being here. Good morning, folks, or actually I should be saying good afternoon to most of you, maybe even good evening. My name is Murat. I'm a customer engineer working for Google, and today I'm going to be talking about AI. It's going to be more of the past and the present than the future. You need to be able to predict the future, you need to understand what we have done in the past and where we are today. It's going to be around 30-35 minutes, and then at the end of the session, we will have some questions. But let's start with some history. The concept of artificial intelligence is not new. Even in the ancient times, philosophers have dabbled with the idea of artificial beings endowed with intelligence. But modern AI, as we know it, is a more recent phenomenon. It's typically attributed to the era of digital computers emerging around 40s and 50s. Actually, there's even an exact time and location when the field of artificial intelligence was founded, introduced to the world. In 1956 in Dartmouth, in the east of US, the most prominent scientists of the day got together. They had a series of workshops, and they have basically laid the foundations of today's artificial intelligence. And these were the people like Marvin Minsky, McCarthy, Frank Rosenblatt. And this is the golden age of symbolic AI with semantic nets, natural language processing systems, but also the first neural networks, connectionism, the perceptrons were introduced back then. Now, as you can imagine, as with any new technology, there was a lot of hype, a lot of optimism, and a lot of money involved. Remember, this is the time of the Cold War, so certain capabilities, such as being able to translate to and from Russian, was quite important, right? It was strategic. It was quite worth a lot. Unfortunately, it didn't work out that well. The machine translation failed miserably. The prime example of that is there was this phrase, the spirit is willing, but the flesh is weak. When you will translate that with those systems, it will become the vodka is good, but the meat is rotten, completely missing the essence of the original phrase. It turned out that the smart people had underestimated the difficulty of the project. That led to what we call the first AI winter. That was around 70s. And there were many reasons for that, right? There was lack of data, right? Insufficiently complex algorithms. We had some algorithms, they were good at toy problems, but they didn't really scale to real world issues. We had limited compute power. There were some natural language processing systems that worked with vocabularies of only 20 words, because that's all fit in the memory. Well, 20 words is nothing, obviously, as you can imagine. And there were even papers by people like Marvin Minsky showing the limitations of the algorithms of the day, like the connectionism, which kind of killed neural network research for a decade. But not long after, around 80s, there was renewed interest, and we had another AI boom. This time, due to a new field called expert systems. These were programs that could solve problems about specific domain of knowledge using logical rules. If you ever used Prolog, maybe, that was the thing when I studied AI a long time ago, you'll know what I'm talking about. These were basically rule kind of infused systems, but they were fragile. They couldn't adapt, so they failed as well. That led to the second AI winter. Things did get better eventually around late 90s as I started studying AI. So this is another example of correlation is not causation. But we did start to get cheaper and faster computers. We had, in the meantime, some breakthroughs with the algorithms. Like, we had the backpropagation introduced, solving some of the problems addressed by Minsky in the 70s. So we could actually do more with those neural networks. And with the dawn of the internet era, we also got access to the ever-growing amounts of data. So, in my opinion, there were three major developments that have caused this acceleration in the advancement of AI as we experience it today. I call that the holy trinity of AI. So kind of talked about this a little, but it starts with data, right? We have now data in abundance. There is, I had some slide in the past. It said we are generating that amount of zettabytes of data every day, but every day that changes. We are generating more and more data every day. When I was studying, again, very long time ago, there was this company that had created a huge cluster of servers. And you know what? That cluster of machines could hold 1 terabyte of that data. That was huge for us. That was called a Tera server. And now today, I have a thumb drive, a USB sticks in my bag that can hold more than 1 terabyte of data. Another thing is that data is now available. We have lots of open public data sets. You can go and download whole Wikipedia, works of Shakespeare. You can download GitHub. So all that information is available for everybody to play with. We also have much more compute power nowadays, right? I'm going to make another reference to my days. When I was building neural networks in the 90s, I would have to train a very simple model, a few hundred nodes, maybe 1,000 parameters, the whole night to train it. But now I can do the same thing in a fraction of a second. We can now, with the compute power of today, can build bigger, better models, and we can train them very quickly. There's also a lot of investment in special hardware, right? We already had the GPUs, but people are now experimenting with more specific hardware. We have FPGAs, we have ASICs, like in Google Cloud, we call something called TPUs, and these are optimized to do matrix multiplications. And if you had a neural network that you were training with GPUs, in months you will be doing it in days with TPUs. That's like, it helps enormously, because the quicker you train things, the quicker you can experiment and can build better and faster new models. We also made some significant improvements to the algorithms that we use. Most of them, we have known them for many years. They're based on, sound mathematics, but we made some breakthroughs in that area. So I'm going to talk about 3 of them, starting with deep learning. Well, deep learning is, in essence, the same as multi-layer perceptrons or recurrent networks, but this time on steroids. They're much bigger, much more powerful. And there have been some improvements in the architectures, right? It's not a simple, multi-layer perceptrons that we are using. We have different architecture, like the convolutional neural networks. We have long short-term memory networks, recurrent neural networks. We have GANs. We have the residual gradient highways. There's a lot of improvements in that area. We also have better strategies. We have different types of activation functions. Rectified linear units are new. We have dropouts, pooling. We have adaptive optimizers. So we have made lots of breakthroughs, even though the fundamental elements are the same as what we have known for decades. And some of that is also these compute improvements, because in the past, again, this is gonna be a bit technical, so if you can follow it, just don't worry about it. But typically, when you work with a neural network, you have a neuron, let's say, an artificial neuron, and it has an activation function. What is an activation function? What it does is that it collects inputs, right? It does a sum of that and applies a function. And it used to be very simple. You had a step function, right? If you go over a threshold, the neuron fires, so output is 1. If it doesn't go over the threshold, it's 0, so it doesn't fire. Kind of basically, that's the idea. But typically, when you use backpropagation and SGD, gradient descent, that kind of models or algorithms, you will have to use activation functions that are differentiable, right? You have to be able to calculate the gradient. So people used to choose for sigmoid functions. And sigmoid functions is a family of functions. There's a lot of different sigmoid functions. And the most used one was the logistic function. And that's something like 1 divided by 1 plus e to the power of minus x. Why is that relevant? Well, the reason that people chose for the logistic function is because its derivative, its gradient, can be calculated based on its activation value. So you didn't have to do very complicated calculations, because that will cost you a lot of compute cycles. That's why people chose for that function. So now today, we don't have to deal with that, right? We have so much compute power, it doesn't matter anymore. I'm not saying that the rectified linear units are more kind of compute inefficient, but it gives you the possibility to think out of the box. Once you have these capabilities, you can try out different things. That's one of the reasons why we are actually making these advancements as well. Another thing, reinforcement learning. So whenever we talk about machine learning, right, we tend to focus on supervised or unsupervised algorithms. When we talk about supervised algorithms, these are quite standard. You have a set of attributes, set of characteristics, set of inputs, as we call them, or features. We have a corresponding output. So we try to find out what the correlation is between those two things. So there's an immediate correlation between them. But there's also a category of problems where there is no immediate correlation between an action and its outcome. And reinforcement learning allows, and it works typically in an environment where you have what we call intelligent agents, right? To learn without presented labeled input and output pairs. It tries to understand what the impact of its actions are. And it does it by, there's this thing called exploration versus exploitation, right? It will try different things, different random elements when you're doing an exploration, or exploitation, then that's going to be more kind of narrow set of actions. But you'll only know whether that action was successful after a while. So it will get a reward on the long-term effect of those. So we have made lots of improvements in that area. We have different algorithms where we can make this correlation on the long-term effects of the actions. Now, this approach has helped us, and this is an example that you see, and you'll see that more often with games, right? And let me explain it a little more with the context of that game. If you move the bar at the bottom, the slider, 1 pixel to the left, you don't immediately know that's a good action or not, right? You'll only know it until the ball hits it and then goes up to hit the brakes at the top. So that you need to find a correlation between that 1 pixel left is the right one at that moment based on all the information that you have. So this approach kind of helped us play better games, but also with robotics, autonomous driving improvements, data center cooling, and even more. And lastly, and this is the most important part because this is very hot at the moment, we have the transformer architecture. And before we talk about the transformers, let me talk about the recurrent neural networks. One of the reasons why we used the recurrent neural networks in the past was that they were able to remember things because their outputs were then refed into the input as the outputs were actually reused as input. So this is important because when you're dealing with natural language, you typically work with a sequence of words, right? And a word will mean different things based on the previous sequence of words. So with recurrent neural networks, what you have is basically you remember what you have learned or what you have done in the previous sequences by using that information back in the model. However, recurrent neural networks, they weren't great. They were slow to train, and they had problem with long-term dependencies, long sequences, due to what we call vanishing gradients. The thing is that when you do back propagation, you take the gradient, you multiply it with some numbers, and then you go back to one layer, you again multiply it. And if you have numbers between 0 and 1, these are typically the gradients you will be getting for instance, for a sigmoid function. If you multiply them multiple times, they will become smaller and smaller and smaller. So if you enroll a recurrent neural network, it's typically many layers. So if you go back to the previous words in that fashion, you will have 0 gradients, so you won't be able to learn anymore. So we have made some improvements. We have introduced, I think almost 10 years ago, the LSTM concept, long short-term memory, and they were designed to address this problem by having more or less what we call memory cells. It did work, but they were still slow, and they had limits when it came to the size of the memory again. Now, in 2017, there was this paper by Google. It was called Attention is All You Need. And it introduced this new concept of encoder-decoder architecture based on attention layers and the transformer blocks. Now, with standard recurrent neural networks and LSTMs, what you do is you typically enter your sequence one word at a time. So it's trained in a sequential fashion. And it has to remember the words one by one. What transformers can do is they will allow us to enter sequences like the whole text, whole sentence, or even bigger chunk of text as a whole, and attribute positional information for each word in that sequence. This already helps us parallelize things, right? Instead of entering the words one by one, we're actually entering the whole set of words at once. Parallelizing means that it will become more compute efficient. Now, we can now enrich each word with positional information, and I'm kind of glossing over some of the details. I'm not talking about how we get information from a word, how we can represent that using word embeddings, another Google thing that we have done in the past. There's a lot of papers around that. Word embeddings is something fantastic where, if you want to, this is an intermezzo again, if you have words, words need to be represented somehow, right? You can have a vocabulary and you could assign a random number to each word. That will work, right? But typically, if you look at numbers, there is some meaning in the scale of them or the difference between them. What you can do with word embeddings is you can assign actually vectors, not numbers, to different words, and the words with the same semantic meaning will end up closer to each other in the vector space. So that's already something that will help you a lot. But I'm kind of glossing over that. So we were talking about the positional information that we use, what we get from the positional encoding layer, and on top of that, we use an attention layer to attribute relevance for each word in that sequence, and that becomes the input for the following layers, which altogether becomes the encoder part, and then a similar architecture used for the decoder part. Now, not all models use encoders and decoders. There are models that are encoder only, such as BACT, right? That's one of the first ones using this architecture. And encoder-only networks are good at next word or next sentence predictions or even classifications, but they're not very good at generating moderate amounts of text. Decoder-only networks can do that better. They can generate, nice amounts of text and can be tuned with zero-shot, few-shot prompts. And encoder-decoder networks tend to be less fluent generators, but can be better at solving understanding tasks. Now, transformers have actually really transformed the world, right? They have become the next best thing in natural language processing problems and has been used extensively in the most of the large language models, from BERT to Megatron Turing to GPT-4 to BARD and what we have today. Okay, now so far we've talked about the history of AI and some of the breakthroughs. Let's look at the current state and maybe the future of things, where we are going. I don't think this is going to surprise you, right? Large language models have been on the rise recently, and their size have been increasing over the years. It looks like it's following the Moore's law, right? It's exponentially growing. And as you can imagine, you can capture more complexity with larger models. If you've ever heard of bias variance trade-off, that'll make sense, right? With high variance, you'll have complex models, you might overfit. But with high bias, you'll have simple, but you might underfit. You'll have to find a balance. And it turns out with these large language models, you have a lot of complexity based on the number of parameters only. We have, I think on this slide, already something you'll be familiar with. Lambda is our kind of one of the most prominent large language models. It has 140 billion, billion parameters, and it's a decoder-only architecture. We have MUM, and I'm going to talk about that as in my last slide. It has 150 billion encoder, and it's an encoder-decoder architecture. And you've probably heard about GPT-3, right? And that one had 175 billion parameters. But since then, we had even larger models, right? There's a lot that has been created by Baidu. There's a lot created by Meta, Facebook's mother company. But Microsoft had Megatron Turing. That's 530 billion parameters. Google had Palm. That's 540 billion parameters, a half a trillion parameters. That is decoder only. So, these are huge things. And if you would compare it to the human brain, right? Estimates are that a human brain contains an average of 90 billion neurons and 1,000 trillion synapses. Now, the GPT-4 was expected to have more than 100 trillion parameters, although it has been released last week, Wednesday, if I'm not mistaken, but there were no kind of words about how many parameters it's using. So we don't know at the moment. It's probably huge. It's probably bigger than GPT-3, but we don't know it at the moment. But the question is, do we need all this complexity? Do we need all these parameters, right? There's this guy, John von Neumann. You probably know, it's one of the founding fathers of modern computing. He claimed that there was this, let me explain the story a bit better. So he had a peer, another mathematician, and he got a prize, an award for a paper he wrote. He had a mathematical model, I don't remember anymore, to predict something, and he got an award for it. But John von Neumann wasn't impressed by it because the model was using 4 parameters. He claimed that he could fit an elephant with only 4 parameters and make its trunk wiggle with the 5th one, right? With more parameters, we can do more, obviously. That was his point, he was trying to say. Also, keep in mind that training large models is not cheap, right? The Megatron Turing model, trained by Microsoft in collaboration with NVIDIA, the rumor is that it has been trained on multiple A100 GPUs, costing around $100 million. So, not everybody can afford that. We do have models that are smaller. We do have the capabilities, and there's a lot that's going to come that's going to make it much cheaper for others to use, but that's more for the future, right? There was also something interesting by another paper last year that was by DeepMind. DeepMind is one of the subsidiaries of Google. It was the Chinchilla paper, another network. It only had 70 billion parameters, and it was doing as well as the much larger models. So it kind of showed that we were more data bound than compute bound. So maybe it doesn't make sense to increase the model size, but rather increase the data, although we might be running out of general domain data. So companies who have access to large amounts of data will be having an advantage. Keep it in mind. Okay. So we talk about LLMs, but what can we do with those things, right? And one of the uses of LLMs can be seen in Google Assistant. I know it's not a new thing, right? It's not futuristic. I've got a video here from 2019. It's already 4 years ago to show some of the capabilities. I don't know if this is going to work.
Hey, Google, open Calendar, open Calculator, open Photos. Set a timer for 10 minutes. What's the weather today? What about tomorrow? Show me John Legend on Twitter. Get a Lyft ride to my hotel. Turn the flashlight on. Turn it off. Take a selfie.
So did you notice how the presenter was making reference to their previous commands? So the system had to take that into account. So it basically, I'm not going to say it's understanding, but it's keeping track of this information, but in such a way that it's natural language specific. It's not really making the person speaking is not saying this or that exactly. So there has to be some sort of, again, not understanding, but being able to reference the other things that have happened in the past, keeping his history available for you. So you probably already have this capability in your phones. So even though it was futuristic in 2019, this is just standard, right? We take it for granted. So let me see if I can go to the next slide easily. Yeah, there we go. So I have another example here, and I've included this because one of the previous sessions I was pitching to somebody who had a product where they had to get a summarization of papers. And it's exactly what it does, right? We have a specific model that allows you to go through a document and make a summarization of that. And that requires really a proper understanding of natural language to be able to do that. So another example. And although this is not the most sexy feature, right? We've come a long way since the flesh is rotten example, when I first introduced the machine translation. The translation models today are more capable and can handle many different world languages. Now, I know that most of you from Central Asia, so I don't know the quality of the models over there, but I do know that we have made a huge leap when it comes to quality of the translation. And these are trained by sentences and documents from the public web. So there's huge amounts of data that we can train on, making it much better, much easier to create these better models. So you've probably heard of self-driving Teslas and maybe some other cars that have that autonomous driving capabilities. All of those actually can't be compared to what we have at Waymo. One of the subsidiaries of Google is Waymo, and they work on autonomous driving. We have cars driving around the US with no drivers at all, right? We are not talking about level 2 or even level 3. This is really truly with no drivers. There are some caveats in there, but still, they do some processing. So no driver has to be present in the car when you take it as a taxi, basically. And I do expect that this feature to be available in maybe 5 to 10 years, like a standard, like we have ABS or radio in your car. You will have this autonomous driving. But the reason I'm highlighting is not because of the autonomous driving, but the data set that we are using to train these models, it's open source. You can get access to it through GitHub. So, if you think that you can do better, you can go ahead and try it out yourself. So again, going back to old times. So for some reason, we've always thought that chess was the pinnacle of human intelligence. So when in 1997, when Deep Blue beat then the world champion Garry Kasparov in chess, it was huge news, right? It was the first time that something like that happened. Although Deep Blue's approach was brute force, right? It could do hundreds of millions of calculations per second to be able to, get to the next move. So some people even compare that approach like bringing a forklift to a weightlifting competition, which is not fair, right? You're kind of comparing human power with a machine, right? That doesn't really make any sense. But that brute force approach doesn't really work for every game. Go is one of them. Brute force approach didn't work for it. So it has been many years before people even attempted the game of Go. In March 2016, there was this model called Alphago, and it defeated one of the best players of the world, 18-time world champion Lee Sedol, for 4-1. And AlphaGo was trained on every recorded game of Go. And we've since then had AlphaZero, which was given the rules of chess, nothing more, just the rules of chess. And with just 4 hours of training, AlphaZero crushed the strongest traditional chess computer called Stockfish, 5-0. Now, just to make you a comparison, AlphaZero evaluates 80,000 moves per second, whereas Stockfish does 70 million per second. That's 3 orders of magnitude larger, right? AlphaZero compensates for the lower number of evaluations by using its deep neural network to focus much more selectively on the most promising variations. So that's why we basically have. By the way, most of these kind of models are not single models, right? They use a combination of these different things. There will be neural networks, some Monte Carlo tree searches, so it's not really a single thing that does it. Just for information. Then we had AlphaStar, built to play an online strategy game called StarCraft. So this is a complicated game, right? Firstly, you play with imperfect information. In chess or Go, you see the whole board, right? Whereas in StarCraft, you can only see small areas around your units. It's also played in real time. Whereas in chess and Go, you do turn by turn, right? And thirdly, it's played with varying and dynamic forces. You don't have 2 bishops, 8 pawns, but you have to decide what to build and attack with. And as you can imagine by now, it did beat the 2 of the top human players 5-0. So, this is all kind of based on the same learnings that we have from the reinforcement learnings and deep neural networks that we've implemented. This is also an interesting one. AlphaCode is another encoder-decoder large language model, but it has been specifically trained on software code. So this is maybe familiar to you if you have ever used GitHub Copilot. It's kind of similar idea. And whenever I talk about this, people ask me, so are we going to replace the software engineers in the future? So I've worked as a software engineer for almost 20 years, and I don't expect engineers to be replaced anytime soon, right? Even in my time, so I was using Emacs, and I had my documentation on the left-hand side. I had, e-tags to be able to find, search for things, oral text kind of based things, my compiler running from a terminal. And when IDEs came around, it made my life much more easier, right? Everything was integrated. There was IntelliSense, and then documentation was integrated. The compiler was integrated. So it made my life much easier by making me more efficient. So this is exactly what I'm expecting from AlphaCode and GitHub Copilot and the likes, right? We are going to become more efficient, and we are going to write better code. We are going to create less errors, less bugs, hopefully. So I do see it as an amplification of our capabilities, not replacement. Okay, this is another one of my favorites, AlphaFold. And before we talk about AlphaFold, I again have a video, and this is talking about the protein folding problem. That's the essence of AlphaFold. So let me first play that, and you'll.
Inside every cell of your body, billions of tiny machines are hard at work. They carry oxygen in your blood, let your eyes detect light, and even make your muscles move. These machines are proteins, and they underpin every biological process in every living thing. Each protein has an intricate 3D shape that defines what it does and how it works. We know of over 200 million proteins and counting, but we only know the exact 3D shapes of a fraction of these. Unravel a protein, and you'll see it's like a string of beads made up of 20 different types of amino acids. Interactions between these amino acids make the protein fold, as it finds its shape out of almost limitless possibilities. For decades, a community of scientists have been working on a way to figure out a protein's shape just from its string of amino acids. This is a major challenge in our understanding of biology. So we created an AI system to solve this problem called AlphaFold. It's trained on the sequences and structures of about 100,000 proteins, painstakingly mapped out by scientists around the world. Today, it can accurately predict a protein shape just from its sequence of amino acids. AlphaFold's predictions could enable progress in all sorts of areas. Imagine a future where we can understand diseases more quickly and develop drugs to fight them, or one where we could use enzymes to break down plastic waste, or even to capture carbon from the atmosphere, all with the help of proteins. There's a lot more work to be done, but unlocking the shapes of these building blocks could help scientists better understand the natural world, and perhaps expand our knowledge of life itself.
So this is truly, groundbreaking in the sense that if you really, if you're able to understand this, we can, predict this properly. It's gonna, change many things. And because of that, there are competitions, right? There have been competitions where, different scientists will come with their own models to be able to, predict, how the shape will be. And the first time that AlphaFold participated in that competition, it did much better than the everybody else. The second version was leaves them bounds ahead of everyone. So a score of 90 and above is considered roughly equivalent to experimentally determining the structure. And AlphaFold 2 scored higher than 80 for many tasks. Still, it's not perfect, but it's much, much better than whatever we have today. In 2022, last year, right, researchers have used AlphaFold to predict the structures of more than 200 million proteins from some 1 million species, covering almost every known protein on the planet. So the data dump is freely available on a database set up by DeepMind. Again, the open source nature of being able to use that information for whatever you need. Okay, we've now seen various examples of how AI models are being used for practical purposes, right? We can recognize, understand, we can even do speech recognition, all that stuff. But how about generating content? Gen AI is also quite popular at the moment. We've got different architectures for generating things, right? We've got GANs, we have diffusion models, but to stay with today's main focus, you can also generate art with transformers. This is something you've probably seen. This is one of the examples, right? There's many of them out there. DALL-E 2 is one of the more popular ones. It can create art from a text description. It can combine, concepts, and its heart is an encoder-decoder model. Roughly simplified, it has a text encoder. So from the text, it generates some kind of understanding. And it has an image decoder, which can translate that text into the image. At Google, we also have a few of these, right? We call them Image and Party. They are the most known ones, but there are also other ones produced by other companies like Stable Diffusion is one of them. They're fun to play with. I know people who have spent hours generating quite interesting things. Yes, ChatGPT. ChatGPT has taken the world by storm, right? It was released, I think, somewhere in December, and everybody was impressed by it. It's a prototype artificial intelligence chatbot developed by OpenAI, and it specializes in dialogue. And the key thing in there was, so the ChatGPT is based on a GPT 3.5 language model. It's an improved version of GPT-3, but the main improvement in there was that it's fine-tuned with both supervised and reinforcement learning techniques to make it to have better conversations, right? It's really fine-tuned for that purpose. And there's a couple of examples of what you could do there. There's a debugging session on the left. I know some software engineers now, instead of going to Stack Overflow or to Google to ask their questions, they go to ChatGPT to debug their things. And there's another thing here. It's a made-up Seinfeld scene that's quite funny to read. But the system can still be fooled easily, right? It has learned that an authoritative style works, right? But it isn't necessarily always right. So there was an example when prompted with why GPUs are better for deep learning compared to CPUs. It gives a reasonable answer. It explains why GPUs are better for that. And then if you claim that DNA computing is better than GPUs and further Abacus is better than DNS, it will confirm, giving reasonably sounding arguments. So it's we need to realize that these systems are not really the intelligence as we know it, right? These are not what we call the AGIs, artificial general intelligence solutions. These are sometimes called stochastic parrots, right? In a demeaning way, meaning that they are here to predict the next word based on all the statistical information that it has collected from huge amounts of data. And it's going to be my last slide, and then we can get to the questions. We talked about transformers. We talked about LLMs a lot, but what's next with those, right? Well, what I see is that there is a emphasis on multimodal, multitask models. Most of the models that we've seen so far are narrow in the sense they can only do one thing, and they typically only work with text. But we have been building models at Google, right? MUM is one of them. It's also based on transformer architecture. It's 1,000 more powerful than BERT. What it can do is that it can interpret images as well as text. So this is a scenario where, there's an example where you wanna, you're a mountain climber, right? You hiked a certain mountain, and now you wanna go to Mount Fuji next fall, and you wanna know how to, prepare. And you can today already sort this out by making multiple Google searches, right? You can look at what Mount Fuji looks like, what's important to know about that, and how is the weather gonna be in fall, and there's the number of things that you'll be doing. But it requires this number of different searches, right? If you would ask an expert, right, that will give you a bit more kind of meaningful, more thoughtful answer with details and things to take into account for your preparation. MUM is exactly that, right? We are trying to get closer to helping you with these types of complex needs. So in the future, you won't need to do many of those searches, but you're just gonna, give this information, and then you're gonna get a much more detailed answer that really fits your requirements. MUM was designed to improve search functionality in the first place. It's been trained on multi-language data, can transfer knowledge between languages, it can answer questions instead of doing multiple searches. And in addition, as I mentioned earlier, not only can handle textual input, but also images, videos, and audio. This is just the slide. You'll see that this is an example of how it deals with with this knowledge. So that's it. That's the last slide I had, and I am happy to take questions now.
Thank you, Murat, for understanding, explaining in plain English this complex stuff. For me personally, it was impressive, especially impressive, this AlphaFold and MUM, the last model family you described. And we have some notorious local data engineers chatting, like Maxim and other people, Hassan, and we have Azizullah prepared questions. And before giving word to Azizullah, guys, you can type your questions in chat, and we will put them on the screen. Please feel free to type questions on this matter. And Azizullah, thank you for preparing questions.
Thank you, Murat. My first question is, with the rise of chatbots and other AI-powered virtual assistants, how do you see the role of traditional classroom teaching change in the future? I mean, do you think chatbots could eventually replace the human teachers?
Okay, that's that's a question that I don't know if you're going to like to answer. But as I said with the software engineering example, I think they're to amplify what we can. I do see them as an additional thing. It's not as a replacement, but as an assistance to be able to do that, right? I still think there is value in personal interactions, but a chatbot could, replace most of the mundane things that you have to do. If you're, working, you're doing your homework, there's something you don't really understand, it would be fantastic to have an assistant that's 24/7 available to give you the right direction, right information to focus on. So again, not a replacement, but supporting.
Oh, okay. Yeah. And my second question is, looking ahead to the next 5 to 10 years, what do you see at the most important trends or developments in the AI industry? I mean, how do you think these trends will impact the way we live, the way we'll work, or I mean, the future?
Yeah, I think there are many questions in there, and how they're going to help us is, I think at the moment we're trying to figure that out, right? We have these fantastic capabilities, and we are trying to figure out which are the good kind of places where we should put it in, where it's going to matter the most. So I do see, most of this capability being integrated in the tooling that we have. Google has announced how we are using LLMs, for instance, in the office, the what we call the modern workspace, or what's it, the Google Workspace suite. How you're gonna get better kind of assistance in when you're doing your documents or anything else that you work on. That we talk about software engineering, where you can use that capabilities. So very quickly, those kind of things. But going forward, it's going to be, my expectation is more and more places. I think our creativity is our limit, right? We can use it for many different purposes. Autonomous driving is one of the things that I hope to have in a few years, but there will be more things that will be replaced by supported by AI. When it comes to the trends itself, well, we've talked about that, right? LLMs, the large language models, are quite popular at the moment. One thing to keep in mind is that, and I already mentioned this, they are expensive to train and also expensive to use. So I think it's going to be quite interesting to see who will have the best infrastructure to be able to run them. So that's another thing that I see a lot of investment in specific hardware for these models.
And I heard. Okay, go ahead.
Thank you. I will just read the question from Cameron Beck. I think local open data resources are limited still in Central Asia. How does this problem affect development of AI, and what solutions you offer? This is a political maybe question, and just to give the context, on other hand, we have, at least in Kazakhstan, international players like AWS Cloud. It's forbidden to store personal citizens of Kazakhstanis personal data abroad unless these cloud providers have physical on-premise servers. This is also part of this problem. Thank you.
No, I understand, and I don't think that there's an easy answer to that, right? I think as long as you have this political situation, right, it is going to be difficult. We do have data centers near the region, right? We have some in Korea, if I'm not mistaken. There are some in Japan, and even in India we have. So from a location point of view, from a latency point of view, there might be some choices you have, but if you really have the rules and regulations, like it has to be in country, we don't have a data center for you. What we do have, and this is becoming a Google Cloud sales pitch, we do have disconnected services, right? And these are basically Google Cloud, I think they're called Google Cloud Distributed or something like that, or disconnected. And this is an appliance that you will be then buying. It will have some of the capabilities that you have in Google Cloud at your disposal in your own kind of local environment. We do have, some customers using that approach. Having said that, that might not be an easy solution for you, but it's going to be important because you will need that compute, right? You will need to have all these capabilities if you want to play a role in there. So either have a conversation with your local governments. I don't know how easy that is, or there has to be investments maybe on your side. And this is, in all honesty, I will. Yeah, it's a tough problem to solve.
Conversations are becoming easier with government. Thank you. And Kamranbek, if we understood your question wrong, please feel free to correct us in this chat. I will read Hassan's question. What are some prerequisites like programming languages, tools, stack to start learning TensorFlow, which is later Hassan added, or for AI in general?
Okay. So TensorFlow is just one of the frameworks, right? There is a bunch of them out there. There is PyTorch. There is scikit-learn if you want to do standard kind of modeling kind of things. So it depends on what you want to do and what you're familiar with. seems like Python is nowadays one of the most popular languages to use, but TensorFlow also comes with C and other libraries. So it kind of depends on what your skills are, what you prefer, what kind of ecosystem that you want to live in. But before you start learning TensorFlow, ask yourself, what is exactly that you want to do, right? What is exactly that you want to achieve? There are ways of building models without really programming. So this is one of the things. I used to work for Microsoft, and Microsoft had this thing called AutoML, right? This is basically you indicate this is your data, and we kind of build the best model for you. It was okay. It wasn't too bad, but it was seen as a baseline for data scientists. At Google, we have AutoML properly implemented. So you indicate this is the data, this is my objective, be it, I don't know, object detection in images, or be it classification or regression, or in time series forecasting. You say, this is the data, this is my objective. I give you a budget of 10 hours, give me the best model based on that. And we go ahead and we really try to find the best model for you using neural architecture search. And we have a model zoo of many different models that we try out. And the models coming out of that, they are very good. I'm not sure if you're familiar with Kaggle competitions. Kaggle is a website where companies organize competitions, right? And people participate and to see if they can kind of win. And AutoML models typically end up in top 10. So it's not easy to beat those models yourself. So if you have a business problem and you want to find out if AI or machine learning in this case is going to help you, AutoML should be your first kind of choice. Try it out. If it works, then you've actually already proven your business case. And then you can think of, okay, now if I want to improve this marginally or significantly, I now have to go and invest in building a better model, but you do know that that's going to take resources and skills and time to do that. So I know that your question was about TensorFlow. I made it a bit broader, but I hope it kind of answers it.
Thank you. It's a great answer. And the question from a researcher from Nazarbayev University, Maxim Popov. How do you think? How far are we from
So
AGI?
today I read something. There was an article about GPT-4. They called proto AGI. So they have seen some examples of what they would classify as AGI. I don't know. I haven't looked into the paper yet. What exactly is the example they are having? I don't know. I'm going to be optimistic about that. It's not going to take too long. I think we are close. We are very close. I mean, and it's not necessarily about the size of the models that we are having right now, but we are making some breakthroughs. We are actually realizing that we can do a lot of things with these stuff. I'll be also interested in whether we need AGI. Do we need that? I mean, there is a lot of things that we can already achieve with the narrow AI that we have. I mean, there's already a great value add. AGI is for me something that you work towards, but that's, in this case, the journey kind of makes it more interesting.
Thank you. Guys, we will probably move to allow Murat to rest because it's almost like 15 minutes.
No worries. No, my pleasure.
Thank you. If someone have maybe one question, I know
let's take last question. Yes.
Okay.
Who wants?
I think I can ask what kind of advice you can give to the people who want to learn, who want to start their career on the AI. It's the most general question.
I think it depends. AI is a large field, right? We've been today talking mainly about machine learning, right? So people kind of equate ML to AI, but AI is bigger than that. There is expert systems, as I mentioned. We have natural language processing without machine learning, although with the LLMs we are using machine learning for that. We have robotics in there. So I think it's going to depend on where you want to be. There are you could be part of the research, right? You could do some very great technology research when it comes to AI. But I think more importantly, it will be great if you would understand or be creative about how you can use that. I think that's more important. At the end of the day, it's nice to have an algorithm, but it's even better to solve a business problem. And for me, focusing on that area, this is something that people miss. And I typically talk to organizations that have very elaborate data science teams, and they have built many models, right? They're proud of it. But I ask them, okay, what are you doing with those models? Nothing. They're kind of collecting dust on the shelf because they haven't thought about holistically about the whole problem. So, okay, it's nice to have that model, but it has to fit in there. Model is just a small part of it. Just imagine that model being part of a solution, right? Addressing a problem. This is where we need your help, right? This is where you should be actually focusing on. Building models is also nice. Okay, that will be interesting if you can do that. But at the same time, think about holistically on how to apply that in a kind of bigger context. That would be fantastic.
Thank you very much, Murat. We have, this is best stream, maybe, I know, for me, I don't know how fast it is, of this year. Still have a ton of questions in comments.
Maybe next time we can do a follow-up, maybe.
Let's repeat this next time, because Piquet, Xenia, and others, sorry, because otherwise it will be like too much load. And it's volunteer. We don't pay to Murat. And,
it's
thank
my
you very
pleasure.
much for your time. Let's
Anytime.
keep in touch. Wish
All
you a
right,
great
folks.
day.
Have a great day. Speak to you. Bye-bye.
Thank you so
Bye-bye.
much.